Hello friends, welcome to my lecture on evaluation of real integrals using residues. We will consider some more cases where the real integrals can be evaluated using the residue method. Let us first consider the real integrals, improper real integrals of the form integral over minus infinity to infinity fx cos sx dx and integral over minus infinity to infinity fx cos sx dx. You might have seen such type of real integrals occur in connection with the Fourier integral. If fx is a rational function satisfying the conditions of the previous article, in the previous article when we evaluated the integral of fx over minus infinity to infinity interval, we had considered fx to be a rational function of x, that is fx equal to say px by qx, where qx does not vanish for any x and the degree of qx is at least 2 units higher than the degree of px. So, we assume the same conditions here on the function fx. So, if fx is a rational function satisfying those conditions, then we may consider the corresponding contour integral. So, we are considering the contour integral over c fz e to the power I sz dz, where s is positive. Now, the contour c consists of the semicircle with center at the origin and radius r, which we denote by gamma, and then it consists of the line segment from minus r to r along the x axis. So, C consists of two parts, one is the semicircle with center at the origin and radius r, which we denote by gamma, and the other part is the line segment from minus r to r along the real axis. So, let us consider integral over c fz e to the power I sz dz and c to be this contour. Then what do we notice is that we can write integral over c fz e to the power I sz dz equal to integral over gamma e to the fz e to the power I sz dz and integral over minus r to r. But when we go from minus r to r, we are moving along the x axis. So, the imaginary part of z is 0, that is by is 0, and we can then take x z equal to x. And so, while moving along the line segment from minus r to r, we put x for z. So, integral over minus r to r e to the power I sx fx dx. Now, let us take, because r is at our choice, the radius of the semicircle is at our choice. So, let us choose r to be so large that all the poles of fz, okay, all the poles of fz which lie in the upper half plane come within the contour c. Okay. So, c encloses all the poles of fz that lie in the upper half plane. Let us take r to be so large. Okay. Then by the residue theorem, integral over c fz e to the power I sz dz will be 2 pi I times sigma residue of fz e to the power I sz, where sigma residue fz e to the power I sz means we find the residue of fz e to the power I sz at all the poles that lie in the upper half plane and take their sum and multiply by 2 pi I to get the value of integral over c fz e to the power I sz dz. Now, integral over minus r to r e to the power I sx fx dx can then be written as 2 pi I sigma residue fz e to the power I sz minus integral over gamma e to the power I sz fz dz. Now, let us take r to go to infinity, then we shall show that integral over gamma e to the power I sz fz dz goes to 0, and once we get this, what will happen then? Integral over minus infinity to infinity e to the power I sx fx dx will be equal to 2 pi I times sigma residue fz e to the power I sz dz. Okay. So, we will have integral over minus infinity to infinity fx e to the power I sx dx equal to 2 pi I times sigma residue of e to the power I sz into fz. Okay. So, what we will do now, we may write this further as integral over minus infinity to infinity fx e to the power I sx we can write as cos sx plus I sin sx dx equal to 2 pi I times. Okay. Now, let us say sigma residue is e to the power I s z f z f z is some complex number, say alpha plus I beta, where alpha is a real part of sigma residue of e to the power I s z into f z, and beta is equal to imaginary part of sigma residue e to the power I s z into f z. Then what will happen when we equate real and imaginary parts? We will have integral over minus infinity to infinity f x cos s x dx equal to now this is 2 pi I into alpha I, and then 2 pi I into I beta will be minus 2 pi beta. So, this will be minus 2 pi beta, because on the right side real part is minus 2 pi beta, and integral over minus infinity to infinity f x sin s x dx will be equal to 2 pi alpha. Okay. So, what we will have, integral over minus infinity to infinity f x cos s x dx is equal to minus 2 pi times imaginary part of, okay, sigma residue of f z e to the power I s z. Okay. Whether we write imaginary part here or we write imaginary part here, the same thing, because we are taking summation later on. So, sigma residue imaginary part of residue of f z e to the power I s z, that is beta. So, that is multiplied by minus 2 pi, and here we have integral over minus infinity to infinity f x sin s x dx 2 pi times real part of this summation or summation of the real parts. Okay. So, sigma is real part of residue of f z e to the power I s z for every z which is a pole and lies in the upper half plane. Now, let us show that integral over gamma e to the power I s z f z dz goes to 0 or goes to infinity. So, mod of f z e to the power I s z is equal to mod of f z into mod of e to the power I s z is equal to x plus I y. So, x plus I y we put here, and then when you multiply mod of e to the power I s into x plus I y is equal to mod of e to the power I s x into e to the power minus s y. Which is equal to mod of e to the power I s x into mod of e to the power minus s y. Now, mod of e to the power I s x is equal to 1, okay, because s is real and positive. So, this is equal to e to the power minus s y, because e to the power minus s y is always greater than 0. So, we will have mod of f z into e to the power I s z equal to mod of f z into e to the power minus s y. Okay. Now, our f x we have assumed to be equal to p x by q x, where q x is not equal to 0 and degree of q x minus degree of p x, let us take equal to d. So, then this d is greater than or equal to 2. Now, in our previous lecture we have seen that when f x satisfies these conditions, then mod of f z is less than 1 by m by r to the power d for sufficiently large r naught, such that mod of z is equal to r and r is greater than r naught. So, and e to the power minus s y, what happened to this e to the power minus s y? Since s is greater than 0 and y lies in the upper half plane, we are in the upper half plane, we are estimating this mod of f z e to the power I s z for this computing this integral, okay, estimating this integral, and gamma lies in the upper half plane, okay, gamma lies in the upper half plane. So, if you take any point on the gamma, then y is greater than 0, okay. So, what we will have, since s is greater than 0 and y is greater than 0, okay, we have mod e to the power minus s y less than or equal to 1, okay, on gamma. this is valid on gamma. Okay. So we can replace e to power minus s by 1. Okay. So this we have m by r to the power d, where d is greater than or equal to 2, and m is any number we have seen greater than mod of an upon bm, where we have taken fx we had fz we had taken to be an z to the power n plus an minus 1 z to the power n minus 1 and so on, a1z plus a naught, and we had taken denominator polynomial to be bm z to the power m plus b m minus 1 z to the power m minus 1 and so on, b1 z plus b naught. Then we had seen that if m minus n is equal to d, okay, and d is greater than or equal to 2, then mod of fz is less than or equal to m by r to the power d, where m is any number greater than mod of an upon bm. Okay. So mod of by Cauchy's inequality. Now let us apply Cauchy inequality. So integrand we have estimated, integrand is less than m by r to the power d, multiply by the length of gamma. So length of gamma is pi r, because gamma is a semicircle of radius r. Okay. So m by r to the power d into pi r, which is pi m over r to the power d minus 1. Now d is greater than or equal to 2, so d minus 1 is greater than or equal to 1, and therefore this goes to 0 as r goes to infinity. Okay. So this is how we prove that this integral along gamma goes to 0 when r goes to infinity. Now let us evaluate integral over minus infinity to infinity cos sx over k square plus x square dx, and simultaneously we will also be able to get the value of the integral over minus infinity to infinity sin sx over k square plus x square dx. Now you can notice here that sin sx is an odd function, k square plus x square is an even function. So sin sx over k square plus x square is an odd function of x, and therefore its value over minus infinity to infinity interval must be 0. So we have to verify that by using residue calculus. Okay. And here this is an even function, cos sx is an even function, k square plus x square is an even function. So cos sx over k square plus x square is an even function. When we use the contour integral over c fz e to power I sz dz, then you notice that we get the value of both integrals simultaneously, value of integral over minus infinity to infinity fx cos sx dx and integral over minus infinity to infinity fx sin sx dx by equating real and imaginary parts. So let us consider the corresponding contour integral here. So let us consider the contour integral over c fz e to the power I sz dz. Now let us notice that here fx is 1 over k square plus x square, and so fx is a rational function of x, where the denominator polynomial is of degree 2, denominator polynomial is k square plus x square. So its degree is 2 in x, and the numerator is a constant 1, so it is of degree 0. So the difference of the degrees in the numerator and denominator is 2. Numerator denominator exceeds by 2 units than the degree of the denominator. The degree of the denominator is 2 units higher than the degree of the numerator. So those conditions, and moreover that the denominator polynomial k square plus x square, which we have denoted by qx, is not 0 for any real value of x. Okay. So we can apply the article which we have just now studied. So let us consider integral over c fz e to power I sz dz, where your c is this integral we are taking over this path c. C consists of semicircle gamma with center at 0, radius r, and the real axis, the line segment on the real axis from minus r to r. So this is our c. Okay. Then we can split integral over c fz e to the power I sz dz is equal to integral over gamma fz e to the power I sz dz plus integral over minus r to r fx e to the power isx dx. Here where fz is equal to replace x by z in the expression for fx. Fx is 1 over k square plus x square. So, this is 1 over k square plus z square. All right. Now, let us take R to be so large, let us take R to be so large that all the poles of fz in the upper half plane lie inside C. Okay. Now, what are the poles of fz? The fz has poles at the points where z square plus k square equal to 0. So, z square plus k square equal to 0 gives you z equal to plus minus I into k. We are given k to be positive. So, ik lies here and minus ik lies here. Okay. So, and moreover that the denominator, if you write qz is equal to k square plus z square, then q dash z, okay, q dash z equal to 2z. Okay. So, q dash z is not 0 at z equal to ik, and therefore, qz has a simple pole at z equal to ik. Okay. So, the simple pole at z equal to ik lies inside C. Let us find the residue of fz e to the power isz at z equal to ik. So, this is residue of fz, fz is 1 over k square plus z square into e to the power isz at z equal to ik. So, we have e to the power isz, denominator polynomial, let us differentiate, we get 2z and then you put z equal to ik. So, we get e to the power minus sk divided by 2 ik. Okay. So, then integral over C by residue theorem, integral over C 1 over k square plus z square e to the power isz dz. This will be equal to 2 pi I times e to the power minus sk over 2 ik. So, this cancels with this and we get pi times e to the power minus sk over k. Okay. So, we have found the value of the integral over C fz dz. Okay. Now, let us go back and see what we have to do now next. So, let us take the limit, let me call it as equation number 1. Let us take r to go to infinity, then this will be, this we have already evaluated. Okay. So, this will become integral over minus infinity to infinity fx e to power isx dx. So, that will be equal to the value of the residue here multiplied by 2 pi I, we got the value of this integral minus integral over gamma. Okay. So, we have thus taking r to go to infinity, we have integral over minus infinity to infinity 1 over k square plus x square e to the power isx dx equal to pi times e to the power minus sk divided by k minus limit r tends to infinity integral over gamma e to the power isz over k square plus z square dz. Okay. So, we can show like we have shown in the article. Let us prove that limit r tends to infinity, integral over gamma e to the power I s z dz over k square plus z square is equal to 0. So, mod of e to the power I s z divided by k square plus z square, let us first calculate this. Okay. So, this is mod of e to the power I s into x plus I y, so upon k square plus z square. So, this is equal to mod of e to the power I s x into e to the power minus s by divided by k square plus z square. E to the power I s x, modulus of e to the power I s x is equal to 1, e to the power minus s y is greater than 0. So, it will not be affected by mod, and then this is less than or equal to 1 over mod of z square minus k square into e to the power minus s by. So, this is 1 upon r square minus k square into e to the power minus s by. Oh, e to the power minus s by, you can let us replace by 1, this is less than or equal to 1. So, we can write 1 upon r square minus k square, since e to the power minus s by is less than 1. Okay. Gamma lies in the upper half plane. Okay. Now, hence by Cauchy's inequality, modulus of integral over gamma e to the power I s z dz divided by k square plus z square is less than or equal to 1 upon r square minus k square into length of gamma, which is pi r. Okay. So, this goes to 0 as r goes to infinity. Okay. Thus, so this goes to 0, this becomes 0. Okay. So, therefore, let me call it 2. Therefore, 2 implies integral over minus infinity to infinity 1 over k square plus x square e to the power I s x dx is equal to pi e to the power minus s k over k. Now, let us put e to power I s x as cos s x plus I sin s x and then equate real and imaginary parts both sides. On the right side you see this is a real value. So, imaginary part is 0. So, equating real and imaginary parts, by putting e to the power I s x equal to cos s x plus I sin s x. Okay. So, we get integral over minus infinity to infinity cos s x over k square plus x square dx equal to pi e to the power minus s k divided by k, while integral over minus infinity to infinity sin s x divided by k square plus x square equal to 0. Okay. So, this is how we do this problem. Okay. So, this is the solution to this problem. Now, let us go to next article. Okay. So, here we consider improper integrals where we have similar points on the real axis. In the previous article we considered those improper integrals where the integrand does not have any similar point on the real axis. It does not become 0. The denominator, we had taken f x equal to p x by q x and we had assumed that q x is not 0 for any real x. So, we considered all those improper integrals where singularities of the integrand do not lie on the real axis. Here we consider an improper integral where singularities will lie on the real axis. So, another kind of improper integral is a definite integral I equal to integral a to b f x dx, whose integrand becomes infinite at a point c in the interval of integration. So, here we will see those kind of integrals where there is a point in the interval of integration at which the integrand becomes infinite, that is limit of mod of f x as x tends to c is infinite and c lies between a and b. So, then we express I as integral over a to b f x dx equal to limit epsilon tends to 0 a to integral over. So, here you see this is your interval a b, okay, and c lies in between a and b. So, we integrate over a to c minus epsilon, this c minus epsilon, integral over a to c minus epsilon, limit epsilon goes to 0 and then c plus eta to b, okay, integral over c plus eta to b f x dx, where eta goes to 0 and epsilon and eta both tend to 0 through positive values independently. Okay. Now, it may happen that neither of these limits exist, this limit or both of them may not exist, but the limit of integral over a to c minus epsilon f x dx plus integral over c plus epsilon to b f x dx as epsilon tends to 0 exists. So, then this limit is called as the Cauchy principal value of integral a to b f x dx, and we write it as principal value of integral a to b f x dx. So, for example, let us consider this example. You see, if you take f x equal to 1 by x cube and the interval of integration we take as minus 1 to 1, then at the point x equal to 0, you see f x becomes infinite. So, now you let us see that the Cauchy principal value exists here. So, Cauchy principal value exists means integral of limit epsilon tends to 0 integral over minus 1 to c minus epsilon, c is 0 here. So, minus epsilon 1 by x cube dx plus we have then integral over c plus epsilon. So, c plus c is 0. So, we get epsilon to 1 here 1 by x cube dx. Okay. So, let us see whether this limit exists. So, this is equal to limit epsilon tends to 0. We have here minus 1 by x to the power minus 3 means when you integrate you get x to the power minus 2 divided by minus 2. So, minus 1 upon 2 x square, and then you put the limits minus 1 minus epsilon plus we have here same thing minus 1 by 2 x square, and you put the limits epsilon and 1, and what do we notice? This is limit epsilon tends to 0. Let us put the upper limit. So, we get minus 1 by 2 epsilon square and then we get plus 1 by 2, okay, when you put x equal to minus 1, and here you get what? Minus 1 by 2 and then you get 1 by 2 epsilon square. So, this cancels with this cancels with this, and the limit is 0. Okay. So, the Cauchy principal value of this integral exists and is equal to 0, but you see the limits epsilon tends to 0 minus 1 to minus epsilon 1 by x cube dx, this limit, okay, this limit and this limit separately if you find they do not exist. Let us see that limit epsilon tends to 0 minus 1 to minus epsilon 1 by x cube dx, this will be equal to when you put the limits you get minus 1 by 2 epsilon square plus 1 by 2, okay, and you take the limit as epsilon tends to 0. Okay. So, this you see that this limit when epsilon tends to 0 through positive values, this gives you minus infinity. Okay. Similarly, when you find limit eta tends to 0 eta to 1, what you get? Limit eta tends to 0 you get minus 1 by 2 x square eta to 1. Okay. So, limit eta tends to 0 and you get minus 1 by 2 plus 1 by 2 eta square, and this becomes plus infinity. Okay. So, both these limits separately do not exist, okay, while the Cauchy principal value exists and is equal to 0. So, we will be considering Cauchy principal value here. In such a case, we can extend, now we will extend the method of evaluating integral over minus infinity to infinity f x dx, where f x is p x by q x, q x is not equal to 0 and degree of q x minus degree of p x greater than or equal to 0. This we have already seen. We will extend the method of evaluating such kind of integrals to functions f z which have simple poles on the real axis by taking the path which avoids these singularities, okay, by following small circles with centers at the singular points. Now, let us see an example on this. Okay, we will first consider the general case. Suppose f z has a simple pole at z equal to a. Okay. So, let us consider the contour, this is gamma. Say suppose I have a simple pole here, okay, at z equal to a, and suppose f z has a simple pole at z equal to a on the real axis, then integrating f z around the contour. So, contour C is now this, this we have, this is semicircle with center at a and radius is epsilon, okay, radius of this semicircle. This radius is equal to epsilon. Okay. So, integral over gamma, we will, when you consider integral over C f z dz, it will be equal to integral over gamma f z dz plus integral from minus r to, now this is what you see here, let me write it separately, minus r r. Okay. This is your point A. So, I have made a small circle here of radius epsilon, okay, and here is your origin. So, minus r to a minus epsilon, this point is a minus epsilon, this point is a plus epsilon, okay, because epsilon is the radius. So, what we do, we have this figure, okay. So, we are moving like this. So, minus r to a minus epsilon, we integrate along the x axis. So, we write f x dx, then integral over gamma, this is integral over gamma, this semicircle. So, integral over gamma f z dz plus integral from a plus epsilon to r, again along x axis. So, we write integral over a plus epsilon to r, a plus epsilon to r f x dx, this is equal to integral over C f z dz. So, you can see by drawing a small circle sufficiently small with sufficiently small radius with center at the point A, we can avoid the singularity at the point A. Okay. Now, letting r go to infinity, let us take r to go to infinity, then and epsilon to go to 0. What we will have? This will become this goes to 0, integral over gamma f z dz goes to 0, integral over minus r to a minus epsilon f x dx plus integral over a plus epsilon to r f x dx, that gives us the Cauchy principal value of integral over minus infinity to infinity f x dx. This value is 2 pi I into sum of residues of f z that lie in the upper half plane, and integral over gamma f z dz we shall see how to evaluate separately. Okay. So, when taking r to go to infinity and epsilon to go to 0, this becomes Cauchy principal value. So, this part and this part tends to Cauchy principal value of integral over minus infinity to infinity f x dx. This we have evaluated by using residue theorem. This will go to 0, and this we will see integral over gamma f z dz, how do we evaluate. Okay. So, everything will be known, and then we will get the Cauchy principal value of integral over minus infinity to infinity f x dx. Now, so let us see here how we evaluate the integral along gamma. Okay. So, this is your figure. This is your figure. this is integral over gamma, this is minus r, this is r, and this is x axis, this is y axis, this is a minus epsilon point, and this point is a plus epsilon. Okay. Now, along gamma, because center is at a and radius is epsilon, so along gamma z equal to epsilon e to the power I theta. Okay. And since we are moving clockwise along gamma, theta varies from pi to 0. Okay. So, along gamma we can write z equal to okay, because center is at a, so it will be not z, it will be z minus a. Okay, z minus a equal to epsilon e to the power I theta, or we can say z equal to a plus epsilon e to the power I theta. So, integral over gamma f z dz will be integral over pi to 0, because theta varies from pi to 0, f z f a plus epsilon e I theta, and dz is z equal to a plus epsilon e I theta gives dz equal to epsilon e to the power I theta into I d theta. So, this is what you get. Now, z equal to a is a simple pole of f z. So, by Laurent series expansion, f z can be written as b naught plus b 1 z minus a plus b 2 z minus a whole square and so on, and the principal part of f z contains only one term, that is c 1 upon z minus a, where c 1 is non-zero. Okay. C 1 is the residue of f z at z equal to a. Now, this part, okay, which contains the positive integral powers of z minus a, non-negative integral powers of z minus a, that constitutes a power series with center at z equal to a. So, that we can denote by gz, where gz is analytic in some neighborhood of z equal to a. So, fz can be written as gz plus c1 upon z minus a, and then integral over gamma. Let us put integral over gamma, let us put in place of f a plus e I theta, a plus f a plus epsilon e I theta, let us put this gz plus c1 over z minus a. So, we will get integral over gamma gz, this integral over gamma f z dz can be written as integral over gamma gz dz plus integral over gamma c1 upon z minus a dz. Now, z is a plus epsilon e I theta, dz is epsilon e I theta I d theta. So, pi to 0 we get this, then c1 times dz is now this, let me write this integral over gamma. So, integral over pi to 0 c1, we have z minus a equal to epsilon e to the power I theta. So, we get epsilon e to the power I theta, dz becomes epsilon e to the power I theta into I d theta. So, epsilon e to the power I theta into I d theta, and we cancel out these. So, we get c1 times integral over pi to 0 I d theta, which is minus I pi into c1. Okay. So, minus I pi c1. This is I epsilon we can write outside, integral over pi to 0 g a plus epsilon e I theta d theta, or I can write it as, let us call this as I1. Okay, this I call as I1 minus I pi into residue of f z at z equal to a. This we have seen here. C1 is residue of f z at z equal to a. So, I can write I pi times residue of f z at z equal to a, and then let us evaluate the value of I1. Now, mod of I1 is equal to mod of I epsilon into integral over pi to 0 g a plus epsilon e I theta d theta. Okay. So, mod of this quantity. Now, gz is an analytic function in some neighborhood of a. Okay. Therefore, integral over pi to 0 g a plus epsilon e I theta d theta, this can be evaluated by Cauchy inequality, mod of g a plus epsilon e I theta, this is less than or equal to m. Okay. You see, we have a semicircle, okay, whose radius is epsilon. Epsilon is very small, okay, and gz is analytic at z equal to a. So, in some neighborhood of z equal to a, this function is continuous, and therefore, and this gamma we can write that mod of g a plus epsilon e to power I theta is less than or equal to m. So, it is bounded in that neighborhood. And now, so this is epsilon, this epsilon we have here, and then m for this, and then e to power I theta modulus will be 1, and then integral over pi to 0 d theta will be minus pi, mod of that will be pi. So, epsilon m pi we have, and so when epsilon goes to 0, I1 goes to 0, and therefore, limit epsilon goes to 0 f gamma limit epsilon goes to 0 integral over gamma f z dz, that is equal to minus I epsilon into minus I pi into residue of f z at z equal to a. So, this is what we get. This is how we evaluate the integral along the semicircle gamma of sufficiently small radius. So, this value we shall put here for this expression, and so we this is equal to 0 when r tends to infinity. This integral and this integral gives us the Cauchy principal value of integral over minus infinity to infinity f x dx. This we know by residue theorem, and this we have calculated. Okay. So, we put the value here, okay, and then calculate the Cauchy principal value. Okay. So, this is we further explain this. So, since this goes to 0 as r goes to infinity, because f z is equal to p z upon q z is a rational function, and degree of q z minus degree of p z is greater than or equal to 2. So, here we use the same thing, that degree of q z minus degree of p z is greater than or equal to 2. Okay. So, thus principal value of integral over minus infinity to infinity f x dx is equal to 2 pi I sigma residue of f z plus pi I, because on the left the integral over gamma was minus pi I C1. So, plus pi I into residue of f z at z equal to a. Now, if f z has a finite number of poles, not we have taken the case where f z has a simple pole at z equal to a. If there are more than one pole, okay, then we will find the residues at all the poles, then we if f z has finite number of simple poles on the real axis, then repeating the above argument for each pole. So, when you repeat the above argument for each pole, what we will have here, this expression, this one will be changed replaced by pi I times sigma residue star. Sigma residue star is the sum of the residues of f z at its poles on the real axis. We showed this formula for the case of a simple pole at z equal to a, but there can be more than one such singularity on the real axis. So, we collect the we find out this residue at all the singularities on the real axis, take their sum and multiply by pi I. So, this is what we do to evaluate the Cauchy principal value of the integral over minus infinity to infinity f x dx. Now, let us consider the case of this integral over 0 to infinity sin x over x dx equal to pi by 2. Now, this integral you can see is not of the type which we have discussed just now, okay, because here the difference is not that of 2 units. How, of course, sin, if you when you will write the corresponding contour integral here, e to the power I z divided by z, then at z equal to 0, which lies on the real axis, the integrand will have a pole, simple pole, but the other condition regarding gamma to go integral over gamma to go to gamma of f z dz to go to 0, that is not satisfied here. So, it is another case, another example where we are going to find the Cauchy principal value, we are going to find the integral of sin x over the interval 0 to infinity. So, what we do, let us consider the corresponding contour integral . And contour is this. Okay, so C is the contour. We can write integral over C e to the power I z dz divided by z equal to integral over, this is gamma, this is small gamma. So, integral over gamma e to the power I z dz divided by z plus integral over minus r2 minus epsilon, because e to power I z over z has a singularity at z equal to 0. So, minus r2 minus epsilon e to the power I x over x dx plus integral over gamma e to the power I z e to the power I z over z dz plus integral over epsilon to r. Okay. Now, let f z be equal to e to the power I z over z. Okay. So, e to the power I z over z does not have any singularity in the contour, okay, C. Okay. So, by Cauchy integral theorem, if you assume f z to be e to power I z over z, then f z is analytic inside and on C. So, by Cauchy integral theorem, integral over C e to the power I z over z dz equal to 0. Let us recall the article. From the article, let us evaluate the integral over gamma. Limit epsilon tends to 0, integral over gamma f z dz is minus pi I residue at z equal to a f z. So, let us follow that. Okay. So, we have limit epsilon tends to 0, integral over gamma f z dz equal to minus pi into I residue of f z at z equal to 0. Okay. And that is equal to minus pi I, because residue of f z at z equal to 0 is limit z tends to 0 z times f z. F z is e to the power I z divided by z. So, this is equal to 1. Okay. So, this is minus pi I. So, thus let r go to infinity and epsilon tends to 0. Okay. Then what we will get? We shall show that integral over gamma e to power I z dz upon z goes to 0 as r goes to infinity. Okay. So, we will have limit r tends to infinity integral over gamma okay, e to the power I z dz divided by z plus limit epsilon tends to 0, r tends to infinity. We have integral over minus r2 minus epsilon e to the power I x over x dx plus integral over epsilon to r e to the power I x over x dx. This should be here because we are moving along the real axis, it should be x. So, it should be like this. Okay. So, this and plus integral over gamma we got to minus pi I, this is equal to 0. Okay. This is what we get. Okay. First we shall show that this value is 0. Okay. So, let us show this is equal to 0. Okay. So, mod of e to the power I z over z along gamma, okay, we have to find. So, e to the power I x plus I y over z, and this is mod of e to the power I x into e to the power minus by divided by r, because along gamma mod z equal to r. So, so mod of e to the power I x equal to 1. So, this is e to the power minus r sin theta divided by r. Okay. Now, integral over gamma e to the power I z dz divided by z equal to integral 0 to pi mod of this, okay, is less than or equal to e to the power minus r sin theta over r, and the mod of dz, dz is equal to r e to the power I theta. So, dz is r e to the power I theta into I d theta. So, dz mod is equal to r d theta. So, we get r d theta here. So, this r cancels. Now, let us notice that by the property definite integral sin pi minus theta equal to sin theta. So, this becomes 0 to pi by 2, 2 times 0 to pi by 2 e to power minus r sin theta d theta. Now, there is an important result, sin theta is greater than or equal to 2 theta over pi when theta belongs to 0 to pi by 2. It is called as Jordan's inequality. It is very easy to prove. We can prove it by calculus. Jordan's inequality. So, this is now less than or equal to 2 times 0 to pi by 2 e to the power minus 2 r theta over pi d theta, and we can now integrate easily. So, e to the power minus 2 r theta divided by pi over minus 2 r over pi. So, this is equal to pi times this 2 will cancel with this 2 and pi over r, and we get 1 minus, limits are 0 to pi by 2. So, we get 1 minus e to the power minus r. Now, as r goes to infinity, e to the power minus r goes to 0 and pi by r goes to 0. So, 0 into 1 minus 0. So, which goes to 0 as r goes to infinity. Okay. So, this is how we prove this equal to 0. Now, what we have, this becomes 0. So, we will get this equal to pi I. Okay. So, now this is nothing but Cauchy principal value, Cauchy principal value equal to pi I. So, we get the following. Okay. So, then principal value of integral over minus infinity to infinity e to the power I x over x dx equal to pi I. Okay. Now, you can put here cos x plus I sin x. So, integral over minus infinity to infinity cos x plus I sin x over x dx. Okay. So, the principal value of this equal to pi I. This means that if you cut real imaginary parts, then this is principal value of integral over minus infinity to infinity sin x over x dx equal to pi. Okay. Now, we know that integral over minus infinity to infinity sin x over x, okay, is a convergent integral. It is a convergent integral. Therefore, Cauchy principal value of integral over minus infinity to infinity sin x over x dx is same as integral over minus infinity to infinity sin x dx. So, since okay, this is convergent, okay, we have cos principal value is equal to integral over minus infinity to infinity sin x over x dx equal to pi. Okay. Now, sin x over x is an even function. So, integral over minus infinity to infinity sin x over x dx is equal to 2 times. Okay. So, since sin x over x is an even function, we get integral 0 to infinity sin x over x dx equal to pi by 2. So, this is how we evaluate this integral. With this we come to the end of this lecture. Thank you very much for your attention.